find just entropy, the average amount of information. What I was talking is about to find, this would be very obvious, but definitely is an interesting a job to find. So to find, okay, to find probability distribution, to be make it more general, or in other words, to find all PIs. Okay, so to find probability distribution that yields the maximum entropy. Okay, so to have that, we have we need to do we need to take the first order derivative of entropy itself, right? And the first order derivative of entropy with respect to each pi, and equate it to 0 and find out that value of pi will give you maximum entropy. Okay, so for obviously for I 1 to n. Okay, all right, so we know that p1 plus p2 to p1 n is obviously sum to 1, and h of m, I'll just rewrite that, minus of summation I1 to n pi log pi. Okay, let's use to take the first order derivative. You have done this in your engineering math as well. Let us use Lagrangian to form a new function. Okay, you'll see the meaning of this. To form a new function, okay, the new function here is, it's a function of all the pi's. Okay, so this gives us a new function which is nothing but h of m itself, which is I1 to n pi log pi plus Lagrangian factor or Lagrangian constant lambda p1 plus p2 pn minus 1. Okay, you'll see the importance of defining a new function in this in this manner, where lambda obviously this term will die down to 0 if there is the mismatch in the sum of these probabilities and to 1. Okay, if there is any the summing up of this is say around 0.9999, so obviously 0.999 minus 1 would be the error involved in the function that we have defined. Okay, so we'll use this Lagrangian a new function utilizing the entropy and the sum of probabilities, and now we'll try to take differentiation of this function with respect to each of those pi's or pj's for that matter, since we have utilized I here. Okay, so this is nothing but the differentiation of the first term. If you carefully look into, I am differentiating with respect to one probability, but keeping all other pi's constant. So to be more specific with respect to the mathematical representation of this is partial derivative of f with respect to individual probabilities pj. All other probabilities except pj will is differentiated to 0, all are constants, and hence I'll be left with simply minus summation of this. So minus, if I take outside, the differentiation of pj times log of pj. Okay, so that means that this is nothing but pj times log of pj, okay, plus lambda times differentiation of pj, which is 1. Okay, the lambda will just simply be retained as it is. So this differentiation is differentiation of uv term, which is pj times differentiation of log of pj, which is 1 over pj. Remember, this is logarithmic to the base 2, and the differentiation is defined with respect to logarithmic base 10, and hence this gets multiplied with log e. Sorry, differentiation is defined with respect to logarithmic to the base e, but the differentiation here, sorry, the logarithmic definition that we have made for the information is logarithmic base 2. Remember that, okay? And hence it gets multiplied with log e minus log of pj times differentiation of pj, which is 1. Okay, so plus lambda is there, of course. So this is true for all j's. All right, so now setting this derivative to 0, this implies, okay, this implies minus log e minus log pj plus lambda is 0, or I can write this as minus of log of e times pj is equal to minus lambda, just multiplying, taking log a plus log b as log ab, and taking this lambda to the other side. Okay, or I can say, of course, these are all base 2's, okay, unless otherwise stated. Please make sure that you know that, okay, log to the base 2, right? So this can be written, each pj is nothing but 2 power lambda over e. Okay, so this is the quantity that we get maximum entropy. So this is for all the j's. Okay, so but we know that, but I'll rewrite that, p1 plus p2 up to pn is equal to 1. This is the constraint that we should be working out with, and these are the j's. P1, p2 up to pn is 2 power lambda over e, because this is true for all j's from 1 to n. This implies that since all these are equal, n times 2 power lambda over e will give you 1. Okay, or okay, this implies that simply p1, p2 up to pn is simply 1 over n. Okay, so this will give you the entropy, the maximum entropy. Therefore, maximum entropy h of m max occurs when, not with, when messages are equiprobable. Okay, remember this is the maximum term. Okay, don't get confused with the negative definition that we have. This is still the maximum amount of information that we will have with likely messages emanating from the other memoryless source that we have assumed in the initial part. Okay, so this entropy may also be viewed as a function associated with a random variable, where the random variable here is the messages with their probabilities. Okay, so you can, in general, we can also write this entropy as, there's a reason this is has, m in its, braces. In general, this entropy can also be written as p of message, which is pi, logarithmic of 1 over p of mi. Okay, we have just replaced this p of mi with pi. Okay, so this is actually the entropy. We can regard this as a discrete random variable, okay, where messages are considered to be occurring in discrete. Okay, yeah. So this is what, I was, trying to explain, where we have now quantified the information. In fact, we have got the messages with us. In terms of digital communication, we can take those messages as a sample of each of those quantized output from the quantizer, and each those quantized outputs are considered to be occurring with their own random probabilities, and our job is to encode those individual quantized outputs to specific bits. In the last session, we said that with few examples, the uncertainty involved in an information or a message is associated with a surprise element. Okay, hence intuitively, the information associated with a message is a measure of uncertainty or unexpectedness. Okay, so this actually, this is a measure of information, okay, which goes with the unexpectedness. Okay, so this is the intuition, or with a layman terms. In an engineering perspective, the measure of uncertainty, okay, the measure of this uncertainty that we saw, we call it as information, which is the message is conveying to us. So this information can be approximated to log of inverse logarithmic of 1 over pi. Okay, where pi is a probability with which that ith message is occurring. Okay, this is the engineering perspective, and hence with this quantitative intuition of the uncertainty or the measure of unexpectedness, we said that the average uncertainty of the source. So with that, we also talked about average uncertainty of a source. Of course, we assumed it to be a memoryless source, of a source emitting messages m1, m2 up to mn. Okay, with each of them occurring with a probability, say p1, p2 and pn. Then the average uncertainty or average amount of information that is carried by all these messages, that we define it as entropy. Okay, we denoted it as h. With respect to the dependency of the message, we can make it more generic as h of m itself, which is actually given as summation over 1 to n pi log of 1 over pi. Okay, this is what we saw, and this is actually basic understanding of the information content in any message. All right, so we also saw that the information content or the entropy of any message is equal to the minimum number of digits required to encode the message. Okay, so and hence the entropy Okay, to make it more concise, the entropy, we also saw that this is the minimum number of digits. To be specific, we said it as bits, number of digits per message. Okay, to encode, uh, to encode the messages. Okay, to encode, okay. And anyway, this is number of the entropy in turn is the minimum number of digits per message required to encode that particular message. Okay, so with that we also concluded that this, for a memoryless, these are all highlights of last session, and these are very much required to take things forward. So for memoryless source, so for source to be memoryless, I had defined it as it emits such messages which are independent of each other. So each message has no dependency on the message that is emitted by the source previous to the timestamp. Okay, so for such a source, for a memoryless source, okay, for a memoryless source, maximum entropy, say I can call this as h of m max, will occur if messages are equiprobable. Okay, so if in the case with unequal probability distribution, obviously the entropy or the minimum number of digits required to represent each of the sample will be definitely less than this the limit of this entropy. All right, so we also saw that if to take things forward, for the source, for the case with, for the case in which source is not memoryless. Okay, so this is an important aspect that we'll be taking forward today. So if this, for the source, if it is not memoryless, then in the event that the source will become memory in the event where messages emitted by the source at any time is dependent on the previous messages emitted. Okay, that's what the meaning of the source being memory, those the source having memory. Okay, then the source entropy, okay, then this implies that the entropy, okay, definitely will be less than the maximum entropy. Okay, okay, so this is only because for the fact that there is a dependency of a message on previous messages which actually reduces the uncertainty. So in intuition way, because the dependency of messages, or there is a, if there is a correlation between each message, okay, reduces uncertainty. When there is a reduction in uncertainty, and there is definitely lesser number of bits are required to represent such messages, each of those messages, and hence it reduces the average number of bits that's required to represent the complete system will also reduce. Okay, and hence it will be, there will be reduction in the entropy itself. So we'll try to prove this, or we'll try to see this in a very in a more intuitive manner.